On the morning of August 6, 1945, at 8:15 a.m., the United States dropped an atomic bomb nicknamed Little Boy on the city of Hiroshima, Japan. This was the first atomic bomb ever used in warfare, and the first of its kind, apart from the gadget which was detonated for a test during the Trinity operation. Being the first, it was largely experimental. The bomb, dropped near the end of World War II, was released from a B-29 warplane flying at an altitude of 31,000 feet. It flew for 44.4 seconds before detonating at an altitude of approximately 2,000 feet, about 600 meters above the ground. The core, made of subcritical uranium-235 masses, was compressed into a critical mass by conventional explosives. The resulting chain reaction caused about 2% of the uranium fuel to undergo fission and convert into energy. Yet, even this small amount of fission was enough to create a colossal mushroom cloud over the city. The ensuing heat and radiation instantly annihilated roughly 80,000 people. All buildings within a 1-mile radius 1.5 kilometers of the blast were leveled. Fires caused by the bomb's heat raged for days, and over 50% of the people in a 4-square-mile area died from burns. For those who didn't face a swift death, radiation poisoning caused them to essentially beg for death. Of course, thousands died under collapsed homes. Thousands more died later from cancer. Children in the region were born with diseases, and by some counts, the total death toll approached 140,000. The effects of this tiny atomic bomb were not limited to a single blast. They were felt for generations. Just 3 days after Hiroshima, a plutonium-fueled atomic bomb dropped on Nagasaki instantly wiped an additional 40,000 people off the map, leading to a total death toll of over 70,000. You cannot even begin to imagine the devastation this caused. But to give you an idea, I'm going to take you to the blast point for a moment. Look, this is Hiroshima before the bomb. This is Hiroshima after the 15-kiloton Little Boy blast. And this is today's Hiroshima. This is Nagasaki before the atomic bomb. This is Nagasaki after the 20-kiloton Fat Man bomb detonated. And this is today's Nagasaki. So now I have a question for you. Why were the atomic bombs detonated high up in the air, about 2,000 feet, 600 meters above the ground, instead of on the surface? For example, the Nagasaki bomb detonated at about 1,650 feet, 500 meters. Have you ever thought about that? Was this a mistake, or was it intentional? We are talking about bombs carrying 15 or 20 kilotons of power flying in the air, but do you truly grasp what that means? And more importantly, what would happen if the most powerful atomic bombs ever created were detonated over cities like New York or Washington, D.C.? To find the answer to our next video's question, can we survive a nuclear attack? Please follow the channel and turn on your notifications. We can generally examine the effects of all explosions under 5 headings: the pressure wave, blast, heat, light, fire, flame, and if the bomb is nuclear, radiation. The impact area of these effects changes depending on the bomb's power and how it is detonated. However, generally all these effects diminish as you move away from the blast center. There are some great websites you can use to visualize this, for example, outrider.org. This site shows what the effects would be if a 300-kiloton hydrogen bomb, the W-87, were detonated over the skies of New York. Consider this. This explosion is equivalent to 20 times the power of the Hiroshima bomb. You can choose from different bomb types on the site. As you can see, we draw concentric circles around the blast point to show the impact areas of each of these destructive factors. I'll return to these circles and simulations in a moment. But first, let's try to better understand the pressure wave and energy dispersed during a nuclear blast. Because atomic bomb explosions are typically recorded from miles away, it can be very difficult to grasp the effects of this pressure wave. Let's look at an explosion we can see more clearly. For instance, when we slow down the high-resolution recording of the ammonium nitrate explosion in Beirut in 2020, we can clearly see the propagation of this blast wave. This shockwave spreads at the speed of sound, which is about 340 meters per second in standard air. However, this speed can change depending on temperature and density. How much energy do you think the Beirut explosion released? While you think about that, I'll show you some explosions you can compare it to. You have probably heard that we measure the energy released during an explosion in units like kilotons or megatons. These all compare the released energy to the energy of trinitrotoluene, or the famous TNT. For example, what does the explosion of 1 kilogram of TNT look like? If you detonated one of those, you would get exactly something like this. If you detonate 1,000 of them, you see this. This corresponds to 1,000 units of the commonly used TNT bomb. The energy of 1 ton of TNT can vary slightly depending on its contents and environment, but it is standardly accepted as 4,184 megajoules. Other bombs are usually classified as multiples of this energy. For example, this blast is equal to 10 tons of TNT. This is also the lowest energy level that atomic bombs can reach. For instance, the smallest nuclear bomb ever produced was a 20-ton Davy Crockett rocket. On the other hand, this shows a bomb worth 100 tons of TNT. This also corresponds to the potential energy an amateur atomic bomb produced for terrorist purposes could potentially achieve. Yes, the smallest atomic bomb currently in the US arsenal is the 300-ton B-61 Mod 3. In contrast, North Korea tested a 500-ton bomb in 2006. While there is no definitive recording, a 500-ton blast looks like this. Finally, if we double that, we reach 1,000 tons, or 1 kiloton. The Beirut explosion released approximately this much energy. The little boy I showed you earlier released the equivalent energy of 15 1-kiloton explosions simultaneously. Since the video recording is not very clear, we can better grasp its magnitude by watching the footage of the Operation Greylock test conducted with a bomb of the same size in 1953. The Fat Man detonated in Nagasaki was 20 kilotons, and as you can see, its video recording is clearer. Many atomic bombs have been tested underwater or underground, so we don't have access to those types of recordings. However, for example, this bomb, the TX-28SE, detonated during Operation Red Wing in 1956, weighed 365 kilotons. At this point, it becomes difficult to even imagine the amount and magnitude of energy the bomb releases, because the camera needs to be placed very far away to record safely. And we haven't even reached the megaton levels yet. Look, this is a hydrogen bomb test produced by the Soviet Union, the 1.6 megaton RDS-37. The camera recording this is currently 70 kilometers away. The test was recorded this way from Kurchatov town, 50 kilometers away from the Semipalatinsk test site. When the shockwave reached 50 kilometers away, you can see soldiers walking on the road being knocked to the ground by the blast. A soldier died during this test in a collapsing bunker. This is actually a very small hydrogen bomb, even though its energy was intentionally halved for this particular test. The first hydrogen bomb experimentally detonated was the 10 megaton Ivy Mike. The largest bomb tested by the US was the 15 megaton Castle Bravo. The largest bomb ever tested by the Soviet Union was the 50 megaton Tsar Bomba. There was a 100 megaton version also developed. The effect of the Tsar Bomba was 1,570 times the combined energy of the two atomic bombs dropped on Hiroshima and Nagasaki. That's 10 times the energy of all the ammunition and bombs dropped during the entire 6 years of World War II. The Tsar Bomba was detonated at an altitude of 2.5 miles, 4 kilometers above the southwest of Novaya Zemlya Island, creating a mushroom cloud with a base 25 miles 40 kilometers wide and a peak 59 miles 95 kilometers high. This mushroom cloud reached 37 miles 60 kilometers into the sky, exceeding even the stratosphere layer of the atmosphere. To put that in perspective, this height was 3 times the record-breaking altitude Felix jumped from. Everything within a 36-mile 58-kilometer radius of the blast point was vaporized. Windows and buildings in Norway and Finland, 100 miles 160 kilometers away, shattered. The light of the bomb was visible from 600 miles 1,000 kilometers away. If you were even 60 miles 100 kilometers away from this bomb, your skin would be scorched with third-degree burns. Look, it has come up again. We said the Tsar Bomba was also detonated at an altitude of 2.5 miles 4 kilometers. To better understand this and the reason for the other details about the bomb, let's assume you are unfamiliar with Japan and detonate the Little Boy bomb over the skies of New York. We will use nuclearsecrecy.com, the first site that comes to mind when you think of an atomic bomb simulation. On the screen now we see what would happen if we detonated our bomb at 2,000 feet, 600 meters above New York, just like in Hiroshima. We can't even truly see the impact area, because the bomb's zone of effect is very small compared to the surface area of New York. However, it becomes discernible when you zoom in on the city. As I mentioned, the circles here show the different effects of the bomb. I want to draw your attention to one point here. Please note that the effects of the radioactive nuclei dispersal, the nuclear fallout that normally scatter after a nuclear blast, are absent in this simulation. Yet, even without fallout, the simulation still projects 263,560 fatalities and 512,000 injuries in the US if this blast happened today. This is a terrifying number. The direct effects of the explosion would be felt by about 10 million people, since everything, including the fuel that powered this bomb, disperses within milliseconds after the explosion. The neutron-sustaining fission can no longer reach the fuel, and there is little else they can affect in the air. Therefore, the effect of an airburst atomic bomb is mostly the large-scale destruction caused by the pressure wave, but the bomb's nuclear impact is much more limited. For example, the Hiroshima bomb only achieved 1.38% fission of its fuel. That means 98.60% of the fuel never reacted. Imagine what would happen if 100% of it reacted. However, if the same bomb were detonated on the ground, there would be many other atoms present, such as from buildings and soil, and because the fuel is usually concentrated at the blast point, more of the fuel would convert into energy, and the nuclear reaction could last longer. For instance, in Operation Plumbob, which I showed earlier, they achieved 73% fission with only a 7-kiloton bomb. Of course, during this explosion, contaminated dust and soil are rapidly ejected into the atmosphere and are carried by air currents, causing heavy nuclear fallout. On the other hand, the destructive pressure effect of a ground-burst bomb is more limited because geographical features like buildings, soil, or hills absorb part of that pressure wave. This is the main purpose of airburst detonation, to maximize the pressure wave damage over a wide area while minimizing fallout. You can also enter the blast height yourself on the site. By the way, you can use the panel on the right to select the locations where the effects of different pressures will reach. For example, 3,000 psi pounds per square inch. That pressure corresponds to a force powerful enough to destroy even missile bunkers. That is 200 times the atmospheric pressure. Just 5 psi, 0.3 atmospheres, only 33% of the pressure you are currently feeling, is enough pressure to demolish most buildings. Setting aside the little boy, even hydrogen bombs, which are more common in nuclear arsenals, like the 340 kiloton B-61 Mod 7, are quite terrifying. If our bomb were detonated in the same way and same location, the effects would be horrifying. As you can see, a bomb 333 times less powerful than the Tsar will not have 333 times less effect, as the energy of atomic bombs does not scale linearly with their effects. As you can see from the summaries, regardless of where and how the explosion occurs, it is safe to say that even a single bomb could bring an end to any country. Even a bomb like the Tsar Bomba, if detonated in a real attack, would plunge not only the country where it was detonated, but the entire world into a dark age. Because such destruction would lead to economic and sociological collapse, in addition to unimaginable loss of life and property. I don't know about you, but I don't think humanity deserves such destruction. We can be a much better species than this. In this video, we didn't discuss what you as an individual should do if faced with such devastation. I will cover those things too. Because now that we know these terrible bombs much better, the only thing left is to learn what we can do individually. See you in the next video. Goodbye.